Hi again. In the last video, we reached this simple expression that we label as equation 1. As we said, it's a balance between the kinetic energy per unit volume of fluid elements that enter this region that we have chosen at the very edge of the liquid sheet or disk, and the resisting pressure due to capillary that holds this momentum and doesn't allow further radial expansion of the jet. To really connect this to the geometrical distance that we observe, we need to find certain functions for h as a function of r and velocity as a function of r in order to be able to simplify this expression even further. One way of thinking about it is using the assumption that is given to us. This liquid is very low in viscosity. Imagine water or a very low viscous liquid. And we can assume flow is almost inviscid. So the only parameters of interest here are density and surface tension. If viscosity is not important and the phenomenon is steady state, we can always think about what we have learned, for example, from module 1, and take one point here, which we call point 1, and follow the streamline of this point as it reaches to the very edge of the liquid sheet at point 2. So we can easily say this concept of Bernoulli principle that in this module for potential flows we have used it extensively can be used here too. So we can use Bernoulli between points 1 and 2. And if we do that, we get a certain simple expression that there is a relatively small change in height. This point 1 can be very much close to the place that jet is hitting the target. And the velocity is Vj there. Pressure is atmospheric everywhere. So pressure is atmospheric here because this is relatively flat if we take this point here. And there is really nothing in terms of pressure changing. So P plus half of rho V squared should remain constant. And on this streamline, the conclusion would be velocity should remain constant everywhere, which would give us V at a position r equal to r should be exactly the same as velocity of the jet Vj. So that's one relationship that we have. The other relationship that we can think of is now that we know velocity in this expanding sheet everywhere is almost identical to the velocity of impacting jet, so it's set by it as Vj and remains constant with the radial position. We may ask ourselves what would be the consequence of that on the height of this liquid sheet, and how does the height of the liquid sheet or the thickness of this liquid sheet, h as a function of r, varies with the radial position. For that, we can again use one of the other concepts that in module 1 we use extensively, and that's conservation of mass. If I think about conservation of mass, what I have is the incoming mass is density times velocity, Vj times the area of this impacting disk, that is the area of the circle with radius rj. So pi rj squared times rho Vj is the incoming mass flux or flow rate that hits my target. Now this mass flow rate should remain constant. So wherever I draw a control volume, this is the incoming mass flow rate, should be equal to the outgoing mass flow rate. And the outgoing mass flow rate, for example, that I have here would be equal to rho times, if we think about it, V at position r equal to r multiplied to the entire area of this edge of this sheet, which is the height of that sheet multiplied to the perimeter of the sheet. So h at position r multiplied to 2 pi r. So that's the balance that we really have in terms of mass flow rate. You can clearly see that now we can replace V at position r equal to r with Vj according to Bernoulli. Densities cancel, so densities cancel. If Vj and V at r equal to r are equal to each other according to Bernoulli, I can cancel them. Pi cancels too. And what I will be left is just a couple of terms. And from this relationship, I can find that h at position R would be equal to Rj squared, radius of the impacting jet, divided by R. So this is another nice relationship that we get from conservation of mass. The height of this liquid sheet is, or the thickness of this liquid sheet is decreasing as I go to larger and larger radial positions. It's said by this relationship is the thickest close to the center, and it becomes thinner and thinner as you radially go away from the center of this problem. Now, what we can call this equation is we can label this as equation 2, and we clearly see a nice conclusion that if I can connect equation 2 and 1 and also this relatively simple result from Bernoulli, which I call a star, I can actually replace these things in equation 1 and get something interesting. So let's continue that here. We combine equation 1 and equation 2, which were conservation of linear momentum, Bernoulli, which is equivalent to conservation of energy in the absence of viscous friction or viscous dissipation. And we can also add, sorry, that was a star, Bernoulli, which is conservation of energy. Equation 2 that I have used is just conservation of mass. So if you think about it, this is conservation of mass, this is conservation of momentum, and this finally, the star equation, is conservation of energy. So we are using all conservation laws in this problem to give us something interesting. The final result, if we combine this together, we will have a relationship for h of r, this expression. We can replace it here. And we can also replace v at position r equal to r with vj according to Bernoulli. And that would give us that 4 times sigma multiplied to r divided by rj squared should be equal to rho vj squared. And with a little bit of algebra, we can show that the r that we were looking after, normalized by the radius of impinging jet, r over rj, is equal to rho vj squared multiplied to rj divided by 4 times surface tension sigma, which you can also write it down as 1 over 4 multiplied to Weber number based on jet, the Weber number that corresponds to the jet. And this Weber number, Weber sub j, is defined as rho vj squared rj divided by sigma. So we actually find a nice final expression, which, as you have seen in many different lectures and recitations in this course, we like to express our final answers in the dimensionless form because nature speaks in dimensionless language. The radial distance that you get normalized over the radius of the jet that impinges on this target is a direct function, is a linear function of the Weber number that is calculated based on properties of the jet, such as density of the liquid in the jet, the surface tension of that liquid with air, velocity of the jet, and the radius of the jet. So it's 1 over 4 of the Weber number. Again, you can see, not surprisingly, there's a nice balance here that is captured through Weber number. If you remember, Weber number is a dimensionless number that takes the ratio of pressure or stresses due to inertia, rho v squared, normalized by resisting stresses due to capillary, which go as sigma over r. That's the balance in Weber number. And no wonder that we get that this balance, how much inertia we have compared to how much resisting capillary we have, will set the final radial position at which the rim stops expanding, or the sheet of the liquid, this disc-like sheet of liquid, stops expanding and starts getting disintegrated into a chain of droplets that fall down. So you can clearly see the use of many different concepts that we have introduced in Module 3 or in previous modules 2 and 1. Conservation of momentum, mass, energy, applying something like a simple contour volume analysis, thinking about line forces that are proportional to the surface tension between two liquids, and how we can actually incorporate them in a contour volume analysis, all getting tied together to give us a nice physical answer that makes kind of sense to our initial intuition, that inertia wants to, or momentum of this impinging jet wants to expand the liquid sheet, and the capillary force wants to finally put a brake on this expansion and stop it at a certain radial distance. You can clearly see in a couple of videos we will show, or a couple of slides, we will show some further aspects related to this phenomena, but you can clearly see before that if somebody measures this radius experimentally, if I measure this radius experimentally and know the velocity of the jet and the geometrical aspect and the density of the jet, the only unknown will be the surface tension of the liquid. So indeed, this setup can be used as a way to measure surface tension of different liquids. You can impinge them on a target. You can take a photograph of this, measure the radial distance at which the sheet stops expanding, and connect that, put that in this relationship, and back calculate what was the surface tension value. Indeed, this was the method that Bond, the person who Bond number is named after, did certain studies in his early work, and he measured or he proposed this apparatus as a measurement tool for surface tension. With this, I stop the overall review that we have done. The next couple of videos will be some nice slides that show different aspects of this phenomena. I hope you watch them with us together, and I hope you have enjoyed the overall review that we have done, and particularly this nice example that at the end we proposed to you. Thank you.